Imagine a star much larger than our Sun nearing the end of its life. This star has spent millions of years fusing hydrogen into helium in its core, shining brightly in the cosmos. But now, it has reached a critical point in its life cycle. The nuclear reactions that have sustained it for so long are coming to an end. It has exhausted its nuclear fuel. The core, once a bustling hub of nuclear fusion, is now running out of the elements needed to sustain these reactions. The outer layers of the star begin to cool and expand, creating a red supergiant. Gravity takes over, causing the star's core to collapse inward with unimaginable force. The core, now composed mostly of iron, cannot support the immense gravitational pressure. This collapse happens in a matter of seconds, leading to a dramatic increase in temperature and pressure. This triggers a cataclysmic explosion. The outer layers of the star are violently ejected into space, creating shock waves that travel through the surrounding interstellar medium. The star erupts in a blinding flash of light. This explosion, known as a supernova, is one of the most energetic events in the universe. For a brief moment, the star outshines entire galaxies, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. This is a supernova, the universe's most powerful and awe-inspiring spectacle. The sheer magnitude of the explosion is almost beyond comprehension, a testament to the incredible forces at play in the cosmos. For a brief moment, a single supernova can outshine an entire galaxy. The light from the explosion can travel across vast distances, allowing us to observe these events from millions of light-years away. It hurls matter and energy out into space at incredible speeds. The ejected material, traveling at thousands of kilometers per second, spreads out into the surrounding space, enriching it with heavy elements. This cosmic event marks the end of a star's life. The once massive star has now been reduced to a dense core, often forming a neutron star or in some cases a black hole. But it also signifies the beginning of something new. The material ejected during the supernova can trigger the formation of new stars and planetary systems, seeding the cosmos with the building blocks of life. Supernovae are not merely destructive events, they play a crucial role in the evolution of galaxies and the universe as a whole. The shock waves from the explosion can compress nearby gas clouds, leading to the birth of new stars. They are crucial for the evolution of galaxies and the universe as we know it. Without supernovae, the universe would be a very different place, lacking many of the elements necessary for life. They enrich the cosmos with heavy elements. Elements like carbon, oxygen, and iron, which are essential for life, are forged in the heart of massive stars and distributed throughout the universe by supernovae. They trigger the birth of new stars. The remnants of the explosion can collapse under their own gravity, forming new stellar nurseries where new stars are born. They leave behind remnants that continue to shape the universe for billions of years. These remnants, such as neutron stars and black holes, are some of the most fascinating objects in the cosmos. These explosions are a testament to the immense power and beauty of the cosmos. They remind us of the dynamic and ever-changing nature of the universe. They remind us that even in death, there is creation. The death of a star can lead to the birth of new stars, planets, and even life itself. They offer a glimpse into the intricate workings of the universe. By studying supernovae, we can learn more about the life cycles of stars, the formation of elements, and the evolution of galaxies. These cosmic events are not just spectacular to observe, they are key to understanding our place in the universe. Stars are giant balls of hot gas, primarily hydrogen and helium. They are powered by nuclear fusion in their cores. This process converts hydrogen into helium, releasing tremendous amounts of energy. This energy counteracts the inward pull of gravity, keeping the star in balance. Over millions or billions of years, a star gradually exhausts its hydrogen fuel. The core contracts and heats up. If the star is massive enough, the core temperature and pressure become high enough to fuse helium into heavier elements like carbon, oxygen, and eventually iron. Iron is the end of the line for nuclear fusion. Fusing iron does not release energy, it requires energy. This creates a crisis in the core. Without the outward pressure of fusion, the core can no longer support the weight of the star. The core collapses in on itself in a fraction of a second. This collapse triggers a shockwave that travels outward through the star. The shockwave tears the star apart in a violent explosion. This is a core collapse supernova. While all supernovae involve the explosive death of a star, there are two main types, Type 1 and Type 2. These two categories are distinguished by their unique characteristics and the different processes that lead to their explosive ends. Understanding these differences is crucial for astronomers as they study the life cycles of stars and the evolution of galaxies. These types are classified based on their light curves, which show how their brightness changes over time. Light curves are essentially graphs that plot the brightness of a supernova against time, providing valuable insights into the nature of the explosion. By analyzing these curves, scientists can determine the type of supernova and gain clues about the progenitor star and the explosion mechanism. Another critical factor in classification is their spectra, which reveal the elements present in their explosions. Spectra are like fingerprints for stars, showing the unique signatures of different elements. By studying these spectral lines, astronomers can identify the chemical composition of the supernova and understand the processes that occurred during the explosion. Type II supernovae occur when the core of a massive star collapses under its own gravity. These stars are typically at least 8 times more massive than our Sun. When they exhaust their nuclear fuel, their cores can no longer support the weight of the outer layers, leading to a catastrophic collapse. This collapse triggers a shock wave that propels the outer layers into space, creating a brilliant explosion. We discussed this process in the previous section. The core collapse is a dramatic event that marks the end of the star's life and the beginning of a supernova. This process not only creates a spectacular light show, but also plays a crucial role in enriching the interstellar medium with heavy elements. These supernovae are characterized by the presence of hydrogen lines in their spectra. Hydrogen is the most abundant element in the universe, and its presence in the spectra of Type II supernovae indicates that the star still had a significant amount of hydrogen in its outer layers at the time of the explosion. This indicates that the star still had a significant amount of hydrogen in its outer layers at the time of the explosion. The presence of hydrogen lines is a key distinguishing feature of Type II supernovae and helps astronomers identify them among the various types of stellar explosions. Type I supernovae, on the other hand, lack hydrogen lines in their spectra. This absence suggests that the progenitor stars of Type I supernovae had already lost their hydrogen envelopes before the explosion. This loss can occur through various processes, such as stellar winds or interactions with a companion star in a binary system. They are further divided into subtypes, but the most common type, Type Ia, originates from a different mechanism. Type Ia supernovae are particularly important in astronomy because they serve as standard candles for measuring cosmic distances. Their consistent brightness allows astronomers to determine the distances to faraway galaxies and study the expansion of the universe. These explosions involve a white dwarf, the dense remnant of a sun-like star that has exhausted its nuclear fuel. White dwarfs are incredibly dense objects, with a mass comparable to that of the Sun, but packed into a volume similar to that of Earth. When a white dwarf is part of a binary system, it can interact with its companion star in fascinating ways. If a white dwarf is in a binary system with a companion star, it can accrete or pull matter from its companion. This accretion process can lead to dramatic changes in the white dwarf's structure and behavior. As the white dwarf accumulates more mass, it becomes increasingly unstable, setting the stage for a potential supernova explosion. If the white dwarf accretes enough mass to reach a critical limit called the Chandrasekhar limit, it becomes unstable and undergoes a runaway nuclear fusion reaction. The Chandrasekhar limit is approximately 1.4 times the mass of the Sun. When a white dwarf approaches this limit, the pressure and temperature in its core become so extreme that a thermonuclear runaway occurs, leading to a spectacular explosion. This reaction completely obliterates the white dwarf in a spectacular explosion. The energy released in a Type Ia supernova is immense, outshining entire galaxies for a brief period. These explosions are not only visually stunning but also play a crucial role in the cosmic cycle of matter, dispersing elements like carbon and oxygen into space, which are essential for the formation of new stars and planets. Supernovae are among the most energetic events in the universe. These cosmic explosions mark the end of a star's life cycle, often resulting in a spectacular burst of energy that can outshine entire galaxies. The sheer power and magnitude of these events have fascinated astronomers and scientists for centuries. The amount of energy released in a single supernova explosion is truly mind-boggling. To give you an idea, the energy released can be equivalent to the energy output of billions of stars combined. This immense release of energy happens in a very short span of time, making it one of the most violent and energetic phenomena in the cosmos. It is greater than the total energy output of our sun over its entire lifetime. Our sun, which has been shining for about 4.6 billion years, and is expected to continue for another 5 billion years, pales in comparison to the energy released in a supernova. This comparison helps us grasp the extraordinary scale of these cosmic events. To put this into perspective, imagine the sun shining brightly for 10 billion years. This continuous energy output, which sustains life on Earth and drives our solar system, is dwarfed by the energy released in a supernova. The sun's energy over its entire lifespan is released in just a few seconds during a supernova explosion. Now imagine all that energy released in a matter of seconds. The rapid release of such an enormous amount of energy creates shock waves that travel through space, impacting everything in their path. These shock waves can trigger the formation of new stars and planetary systems, demonstrating the cyclical nature of the universe. That's the energy scale of a supernova. The energy released is not only vast but also incredibly diverse, spanning the entire electromagnetic spectrum. This diversity in energy forms is what makes supernovae such fascinating objects of study for scientists. This energy is released across the entire electromagnetic spectrum, from radio waves to gamma rays. Each type of radiation carries different information about the supernova, helping scientists understand the underlying processes and the nature of the star that exploded. This includes a tremendous amount of visible light, which is why supernovae can be so incredibly bright. The visible light from a supernova can be so intense that it can be seen from millions of light years away, making it a beacon in the night sky. In fact, for a brief period, a supernova can outshine the combined light of all the other stars in its galaxy. This temporary brilliance is a testament to the immense power of these explosions, which can dominate the light output of an entire galaxy. The energy released in a supernova is not just light, it includes a wide range of other forms of energy, each playing a crucial role in the aftermath of the explosion. This energy can influence the surrounding interstellar medium, leading to the creation of new cosmic structures. A significant portion of the energy is carried away by neutrinos, tiny, almost massless particles that interact very weakly with matter. These elusive particles are produced in vast quantities during the core collapse of a supernova, providing critical insights into the processes occurring at the heart of the explosion. These neutrinos escape the exploding star at nearly the speed of light, carrying with them information about the core collapse. By studying these neutrinos, scientists can learn about the conditions inside the star just before it exploded, offering a glimpse into the final moments of a star's life.